Okay, hello. This is Jian Zhang from Intel. Today I'm going to talk about the challenges, opportunities, and the lessons we learned from the real-life clusters in China for the open source storage in OpenStack Cloud. So this is a brief agenda. The first we will give a brief introduction of who we are, what we do. The second thing is give a brief overview of the OpenStack and the open source storage in PRC. Following that, I will talk about the stability challenges, the performance challenges that we have met, and what we have done to optimize the performance. So you probably know that we have 3D cross-point and a 3D NAND product will come soon. So we are trying to do some kind of a POC findings to try identify some opportunity to optimize the storage solutions. So we are the Intel Cloud Storage team. So we deliver optimized open source storage solutions on Intel platforms. So most of our team, we work on Ceph. We do a lot of performance analysis. We have a performance portal called 01.org performance portal, which will kind of deliver the performance of each major releases. We have developed a lot of tools and BKMs like CTune, which is CephTune to automatically deploy, benchmark, analyze, and presenting the Ceph performance. We also have Virtual Storage Manager, which is UI-based management tool. We also have CostBench object storage benchmark tool. So we have come up with a lot of performance tunings and BKMs. So if you are interested, you can welcome to go to the Intel booth to look at our all-flash array reference architecture and how we achieve like 1 million RPS. So the third thing we do is actually customer engagement. At Intel, we actually support like 35 plus customers to help them enable Ceph-based open source storage solutions. So let's take a look on what's the OpenStack and the open source storage status in China. So personally, I'm thinking China is seeing as a massive opportunity for most of the cloud computer vendors. So the China cloud computing infrastructure investment will grow faster than the overall IT spending. And the government they have announced officially that OpenStack is a key strategy for it. And the second thing is we do see that there is a strong demand on the open source storage in PRC market. So Ceph is even hotter in the China market compared with the rest of the world. So this is the Ceph community we grow. So working with Red Hat together, we kind of build two Ceph days. One is in Beijing, the other one is in Shanghai. So what we see is a lot of companies, they are doing kind of a redeployment based on Ceph. Based on the upstream code, and more companies, they are moving to open source storage solutions. So for the two Ceph days, it attracted like 350 attendees from like 250 companies. So the media, they come up, they do some kind of self-media report and reclipping. So we can see that there are more and more PRC code contributors in the community, like from ZTE, XGuy, H3C, RETV, United Stack, and eBay. So let's take a look on the first challenge, the stability challenge. So if we take a look on the issues, we heard most from the customer. Actually, there are two major problems. The first one is the OSD flapping. So when your OSD goes up and down again, the second thing is the slow request. So we did some analysis on this. We also did some optimization. The first thing is for the OSD flapping. It turned out that currently the heartbeat is doing a very reasonable way. For example, if you have a physical host that have like 9 OSDs, each OSD still have the chance to vote down other OSDs if that physical node network was disconnected. So what we do is we propose kind of a smart failure detection mechanism. We will level the cluster map to do a smart failure detection. So if most of the OSDs they are from the single physical host, it's likely that that host itself is a problem, not the problem of other OSDs. So this is the first thing. The second thing we try to convert the OSD stability time, so we will shut down the flapping after certain times. Second thing is we don't try to boot if we have no available peers. And this is pretty much the optimizations on the OSD flapping. So let's take a look on the slow request. So slow request is kind of a log dumped from a message dumped from log. So when your cluster is experiencing some kind of a performance issues, usually there will be a log in the Ceph log that tells that there is a request that is exceeded the timeout value. So it's kind of a dump slow request. So the following table is actually the the possible causes and the possible solutions from the Ceph.com. But probably most times these don't work. So it kind of looks like we need a better mechanism to detect what caused the slow request. But this kind of beyond OP track's scope. Slow request is only a phenomenon that the OP tracker will track each request. If it exceeds the timeout value, it will dump a slow request message. So it turns out that some other things can be better, doing better job in this case. So we can do how do we leverage the smart info? For example, if we can detect the hard drive fail, if we can detect there is a file system issue, so we can predict the partition errors. So we can leverage some third-party management software to better handling those kind of errors. The second thing is, if we want to detect most people, they want to detect the failure in a fixed time. They don't want to the cluster status, they up and down again. So this is still another thing we need to do. And the second thing is how can we sort the state convergence time? So most of the slow requests actually it only asserted the error. There is no such kind of a nested failure handling thing. So if we can encode the error with better encode, so we can the upper layer application or the management software, they know exactly what kind of a failure happens, so they can handle that failure more efficiently. The third thing is we can expose more messages about the failure types from the log, like is it a file system error, hardware error, or network error. The last thing is actually how to troubleshooting it. So when people match this problem, usually they don't have any chance to read the log because it depends on the knowledge of the administrator or the developer. Only they can read that kind of log. So maybe there is a third-party software that can better translate the error message to something more to better understand it more easily. This is the stability problem. Then let's take a look on the performance problems. So this is really about Ceph on all-flash array. Probably you may have a question that why people are using all-flash array in Ceph. Why don't they go to SCIO? So what we are seeing is that the storage providers that are struggling to achieve the required high performance. They are building OpenStack-based public and private cloud. They still want to compete with AWS. So in that scenario, they really want to build a high EBS-like service that's with high performance. The second thing is there is strong demand to run enterprise applications in Ceph. So we do see that, as we all know, that Ceph is the #1 block storage backend for OpenStack, and there are more and more people running OLTP workload, MySQL stuff. So they are running those kind of high performance requirement workload in Ceph, and this is the first reason why they're using Ceph. The second thing is actually even the performance is not as high as they expected. So they can try the multi-purpose advantage. For example, they can build a huge MySQL cluster, which is more easy to management. They can get kind of a flexibility there. But we need to admit that performance is still an important factor. So what we do is we do a lot of tunings and optimization here. If we take a look on the 4K random read and write performance, the default performance is really low. But with various kind of tuning and optimizations, we can increase the performance like 16 times. So take several examples. The first one is usually when you deploy a hard drive cluster, you will deploy a single OS instance on each hard drive. But in SATA SSD's case, you may probably need to deploy 2 instances. But if you are using NVMe SSDs, the best known number is actually 4. Second thing is we definitely need to turn off all the debug levels to achieve the best performance. The debug level really have a big performance impact in the all-flash array configuration. The second thing is the third thing is about the memory allocator. The default memory allocator is tcmalloc, but it's not. There is some problem with the old version of tcmalloc. The cache size is really small. If you are running too many threads, it will do a lot of context switch between those threads. So the system is doing nothing but instead of the context switch. So we simply switch it to gmalloc. We can see it's like 6 times performance improvement. And the other thing is really about the OSD OP thread tuning and the RBD thread tuning. So with all those kind of tunings, even on the all SATA SSD, we can get like 1.08 million RPS for 4K random read. But for the write, we can see currently the peak performance like 140K RPS. It's kind of like 60% of the raw hardware capacity. Still have some improvement rooms. So the last thing is, based on the analysis, we want to try to find something we can do with the future hardware. I mean 3D NAND and 3D crosspoint. So this is 3D NAND. In the future, I mean the SSD, the density will be much higher, and the cost will be much lower. So we are actually expecting when 3D NAND comes out, the cost per gigabyte will be much closer to the high-end SAS drives. And for the 3D crosspoint, probably you have heard of that. It's like 1,000 times faster than NAND. It's 1,000 times of endurance of NAND, but and it's 10 times density of DRAMs. So let's say the opportunity here. Most people, if today we are still using file store backend, maybe they want a cost-effective solution. So this is the above picture is actually the reference architecture we are using now based on 1P3700 NVMe SSD as a journal, and for S3510 SATA SSD as a data disk. So in this kind of a configuration, we can get 1 million RPS, and the performance is really like 175 times of HDD cluster. In the future, when 3D NAND and 3D crosspoint comes out, we could leverage the 3D crosspoint device as the journal device, but we upgrade those SATA drives to the PCIe 3D NAND-based drives. It will be 4 terabytes soon. So in this single box, we can deliver 20 terabytes all-flash Ceph node, and which the performance is really higher, and the cost is much closer to the above configuration. So this is a comparison we did for this SSD cluster to compare with the HDD cluster. So we simply did some mathematical calculation here. We try to, there are a lot of assumptions, so we kind of say, trying to see how many HDD nodes we need to achieve the similar performance with this HDD cluster. So we can see for the 4K random write, the all-flash array cluster is like 58 times of the HDD cluster, and for the 4K random read is actually 175 times of the HDD cluster. So the cost is really, the cost advantage is really obvious in this scenario. So here comes the summary part, which I mean, Ceph is more and more popular with OpenStack growth in China, but we do see a lot of challenges from the customer about the stability problems, the reliability problems, and the performance problems. So Intel is working with the community to improve Ceph performance and doing a lot of path-finding jobs based on our 3D crosspoint and 3D NAND products. Okay, thank you. That's all.